Problem number 15. In the device shown, blocks of various masses are placed on a distance so that the device is in equilibrium. The fluid in the drawing is to scale. There are valves that are both initially open at locations A and B. One of valves is closed and the system is allowed to come to equilibrium. How will this affect the height of the mass M2? Solution for problem number 15. The gauge pressure of the water directly on the block M1 must be M1G over A1, where A1 is the cross-sectional area of the tube containing block M1. The pressure in the horizontal section of the tube is therefore ρgh plus M1G over A1. But by the same reasoning, the pressure is also ρgh plus M2G over A2 and ρgh plus M3G over A3. Now we conclude that M1G over A1 equal M2G over A2 equal M3G over A3. This is the condition for equilibrium in the device. Now, if we close valve A, the condition for equilibrium in the right two tubes is M2G over A2 equal M3G over A3, which is already met. So these tubes remain in equilibrium. The same applies to valve B. In other words, the pressure is the same to the left and right of the valve. So closing the valve doesn't affect the equilibrium. So it means that right answer is A. Closing either valve will have no effect on the height of M2. That was a solution for problem number 15. Problems number 16 and 17. The following information is relevant to problems 16 and 17. A mass big M sits on top of a vertical spring of a spring constant K in equilibrium. A mass small m is held a height h above it. The mass big M is then pushed downward by a distance dx, and both masses are released from rest simultaneously. For what value of h will the two masses first collide when big M first return to its equilibrium position? Solution for problem number 16. First, let's write the equation for time to move for big mass M from bottom part to equilibrium. That will be a quarter of full period, which is pi over 2 multiplied by square root from big M over G. Second, this time equal time to fall down for small mass for distance h. That will be square root from 2h over g. And now we just need to equalize this two times for two masses to meet in equilibrium position. That will be this equation, and from here we can find what is height h. That is pi square big mg over 8k, which is answer D, and that was solution for problem number 16. Problem number 17. Assume that h takes the value found in the previous question, and that the collision between the two masses is perfectly elastic. For what value of dx will m small rebound to a maximum height that is exactly equal to its original height? Solution for problem number 17. for small mass m to rebound to the same height, it must go after collision with the same speed that it was right before collision. It means that two masses must collide with the same momentum to get the same speed with the opposite directions. So it means that we have equation m small multiplied by vm small, which is speed of small mass right before collision. That's equal to m big multiplied by vm big, where vm big is speed of big mass right before collision. Both velocities we can find from energy conservation. For big mass we have potential energy for spring must be equal to kinetic energy for big mass, so that will be this equation, and from here we can find what is V big M. That's dx multiplied by square root from k over big M. For small mass we can just count what is the speed of this mass after free fall for distance h, which we just counted in previous problem. That was this expression, and now we can count what is speed for this small mass. That is this equation. And now we can put in the first equation our expressions for these two velocities. That will be this equation, and finally from here we can find what is dx. That will be p small m g over 2k, which is answer E, and that was solution for problem number 17.